Thanks for the introduction. Can you hear me well? Okay, perfect. Yeah, so you can see the title here already, but before starting I would like to add a few more words on my affiliation, Fraunhofer IISB. Actually starting with the Fraunhofer Society as a whole. So yeah, the Fraunhofer Society is a research society mainly based in Germany, although there are also worldwide research centers. And the main focus of Fraunhofer is doing application-oriented research, so really bringing research into the industry. As Enrico already said, my institute, the Fraunhofer IISB, is located here in Erlangen and has two main focus areas, which are wide bandgap semiconductors and power electronic systems. And within these within these areas, we are tackling a lot of applications ranging from electromobility, aerospace, energy supply, and so on. Also within these applications and field of researches, we are covering the entire value chain, so starting from material level, analyzing crystal growing for semiconductor materials, up to devices, packaging, up to actual power or energy systems. Okay, that's the institute in general. Also, the institute has one department specifically dedicated to modeling and AI. So the aim of this department is to support all the research areas within our institute with hand-tailored digital solutions, basically. And yeah, the head of our department is also here, Andreas, who's sitting here in the third row. And yeah, the department is structured again into three groups. The first one is focused on semiconductor-related simulations of different types. So, for instance, device simulations, so simulating devices and their electrical characteristics. Also quantum devices and other semiconductor-related processes like topography, for instance. Then secondly, there's one group specifically dedicated to lithography. So in particular, EUV lithography, which is essential for state-of-the-art semiconductor manufacturing. And in this group, they are doing the modeling of these processes as well as developing solvers for them. So they have a state-of-the-art solver, Dr. Litho, which is by now GPU accelerated and is really the state-of-the-art in this field. And lastly, the group I'm also working in is the AI augmented simulation group, which yeah, you can think of being at the intersection of computational engineering, math, and AI. One main part of this of the research of our group is scientific machine learning, which is basically also the area I'm mainly responsible for, and you will learn about this in more detail soon. Other fields of research include simulations and reinforcement learning techniques in power electronic applications, and also quantum computing. All right, but that's that for my affiliation. Now let's talk about the methods we use in the field of scientific machine learning in more detail. And to start, let's think on like a top-level perspective on different way you could use to simulate a physical system, say given by PDEs. So the classical way, in a sense, is to do this via numerical methods, right? For instance, the finite element method or also other ones, where the idea is that you take your physical laws and discretize them in order to compute your solution, basically, right? So the modeling is really based on the physical laws. However, in particular in industry applications, this might be computationally expensive or computationally too expensive, in particular if you want to do a lot of simulations. For this reason, also in the field of simulations, more and more machine learning techniques are used. And here by machine learning, I really mean machine learning in the classical sense based on data, right? So the idea is to train some model, some neural network, which is usually very fast to evaluate once you've trained it. But in order to train it, you need a lot of data. And of course, you need high quality data if you want to have a good model. Okay, so these are sort of the most common ways you can do. Here in this talk, I want to focus on something which you can think of lying in between of these two topics, which is physics-informed machine learning. So there the idea also is to train a neural network similar to the machine learning approaches, but the training should not be done via data, but directly from the physical laws. So you again get the physics-based modeling similar to numerical methods, but also get fast to evaluate models once you have trained this. So this term, physics-informed machine learning or physics-informed neural networks, I'm sure that many of you have heard this before, and the main reason is this paper here, which used this term PINs, physics-informed neural networks first. And yeah, below you can see the total number of citations at the end of each year. So you can definitely see that there's some hype about PINs. Whether that's a good or a bad thing, you can decide for yourself. But definitely the method is very popular. For this reason, as I said, I think that many of you have heard this before. Nonetheless, if you have not, then I will try to explain the main idea of this method here on this one slide. If this is still unclear after this slide, please stick with me nonetheless, because hopefully this will become also more clear when we discuss specific applications we are applying these methods in. Okay, but for the main idea, let's focus on this sample example here, where we are considering the Poisson equation on a unit square with some given right-hand side f and vanishing Dirichlet boundary conditions. Okay, if you want to solve this problem now via physics-informed machine learning, then the first thing you do is you represent your sought solution as a neural network, right? So basically the answers you're making for your solution is a neural network. Why is this a good idea? Well, one main benefit these neural networks offer is that they are very efficient to differentiate. I mean, this is what you usually do when training the network, so when adapting the parameters of the network. But of course, you can do the same thing also with respect to the input coordinates of your neural network. Okay, once you can differentiate it, you can use this to assess how well your current neural network solves the PDE, right? This is done here in the first line, where you can see that I've just taken my Poisson equation and have rewritten this in this residual form here. So if you evaluate this, this first expression here onto a lot of points within your spatial domain, then if this expression is close to 0, then your neural network satisfies the PDE to a good extent or with high accuracy. And the same is also true for these other terms here corresponding to the boundary conditions. So if all of these terms are small, then all of your physical laws are satisfied accurately. And hence what you do is you combine all of these terms into one single loss function, usually by just summing them up. And in this way, you get an overall measure of how well your neural network satisfies all the physical laws simultaneously. Well, in this loss function, you can then just use to train your neural network's parameters, right? So if you minimize this loss function, then you obtain an accurate solution of your system. And that's the main idea, right? And two things I want to emphasize here is, firstly, you don't need any data for this whole workflow, right? The only data or the only information you're using for the training are directly the physical laws in this form I've stated here. Secondly, I should emphasize that in the form this is currently stated, this really is a physics-informed neural network, meaning that this only gives you one particular solution of your system. So for instance, if your right-hand side of the Poisson equation changes, then you need to retrain your neural network. Often this is not sufficient because you want to analyze a larger class of solutions, but this you can also do by also integrating the right-hand side, in this case f, to the input space of your neural network. In this way, you obtain what's usually called a neural operator, because this really gives you a mapping into the whole solution space of your problem. Okay, so that's my one slide attempting to explain the main idea. I hope you agree with me when I say that the main idea of physics-informed machine learning is rather simple, I would say. Nonetheless, actually getting an accurate model of this form is rather challenging, in particular in industry-relevant applications. And the main reason for this is that there are a lot of things you have to take care about and that you have to get right. For instance, you have to choose the right neural network structure to represent your solution, right? Ideally, this is adapted to the physical problem you're solving. And of course, there are a lot of types of neural networks you can use for this. Secondly, you have to provide the governing equations in a suitable form to the neural network. So on the previous slide, I've just used this residual form, but often there are a lot of equivalent forms of the PDEs. You can use weak or variational forms, which may be better suited to the training. and this you need to consider. And lastly, and maybe most crucially, is the optimization or the training process of these neural networks. I mean, if you compare the scheme to classical machine learning, now the loss function contains differentiation of your neural network, right? So in a sense, this is of a higher order than classical machine learning approaches, where you just aim to match the output in some specific cases to prescribed values. So for this reason, the training is often an issue in this application. Hence, you need to choose good optimizers to do this. You need to find a good balance between different optimization tasks, for instance, the PDEs and the boundary conditions in our previous case, and need to identify suitable settings to sample during training and also further stuff, right? So takeaway from this slide is there are a lot of challenges you have to overcome, but still this can be done. And this is also the motivation for my talk here, that I want to discuss some applications in which we successfully applied this method. And I want to show you for each of these categories what worked for us in each of these applications to give you an idea of what you have to do to get accurate models of this form. Physics-informed Kolmogorov-Arnold networks. So CAN is Kolmogorov-Arnold networks. So neural networks based on the Kolmogorov-Arnold representation theorem. Yeah.
And is it worth to try the extra effort that this requires with respect to beams?
There are definitely some works in applications where this worked better than usual MLPs, these CANs. And they offer certain advantages, like they can be interpreted better because you can prune them in a better way and stuff like this. So for interpretability in particular, this is definitely worth a try. Also accuracy-wise, they excel in some cases, but not at all, I would say. So this depends on the problem. All right. If there aren't any further questions at this point, then I would proceed with the first applications I wanted to discuss in more detail, which is from the field of nano-optics and is mainly conducted by my colleague Vlad, who also is here with us today. So what you want to analyze here are so-called optical metasurfaces, and they are illustrated here. So an optical metasurface is this yellow region here, whose task is to manipulate light you shine through, basically, right? So you have some input light, this incident light here below, and as it passes the metasurface, it changes some of its properties. So for instance, this might include the transmittance, so how much light actually passes through. This might include a phase shift in your light wave and also further properties. And these devices, these surfaces, they are in fact essential in augmented reality or virtual reality devices, also in sensors and LiDAR systems, and also further applications this is used, or this heavily relies on these surfaces. Okay, so usually your task in this application of optical metasurfaces is that some, say, an engineer describes to you, okay, I want to have an optical metasurface with given properties of the transmitted light. So you want to have usually a high transmittance, so a large amount of light passes through, and you want to have some prescribed phase shift of your light. And your task then is to design a metasurface which has these properties. All right, to do this, the first step, of course, is to build an accurate forward solver, right? So you need to understand, okay, if you have some input light into a metasurface of a given structure, how does the output light look like? Well, how does this manipulation go on? And this is the first thing that we want to look at in more detail, and here I want to present to you how this problem is modeled mathematically. So, as I said, the main input of the model are the metasurface, in particular its structure and its material properties. And all of these information, they can be stored in a single function on 3D space, which is complex valued, the so-called permittivity function. So this contains basically all the information of your metasurface. Secondly, the input for your model are the properties of the incident lights.
Sorry, this metasurface, you know it?
In this case, so in this first forward problem, we know it, but afterwards we also want to design it to match given properties. But at the moment, we're just focusing on the forward problem where we assume that we have a given metasurface and just want to see how the light is manipulated by it.
And then the incident light is something also you can regulate yourself?
Yes, so usually on the application you want to have given properties over a light, over a wavelength range, right? So you want, for instance, okay, the red light has to be inhibited in this way and blue light in another way, for instance.
But you have tools to make this experiment covering all this range? Or?
Yes, so the range you can adjust basically in the experiments, yes. All right, so these are the input properties basically, the properties of the incident light, for instance, also the incident angles, on which angle it's approaching the matter surface, and the wavelength and the permittivity storing the information of the matter surface. And all of these inputs, they enter our model, and this model for modeling the transmitted light is mainly based on the 3D Maxwell equations here in the first line, here written in the vectorial form. So actually these are 3 equations, all of which are complex valued. And you can see here in the second term on the left-hand side that also the permittivity and the lambda, the wavelength of the light, enter this equation. In addition, you have some boundary conditions which are not too important here, so they are similar to periodic boundary conditions, for instance, the outer parts, and some absorbing boundary conditions at the top and the bottom. And also another way of how these parameters enter the system is via this incident field here. So your total electric field is the sum of a scattering field, which is the actual unknown of the system, plus something which is explicitly given by the parameters. It appears here in the incident field. All right, so if you can solve this system, then you can obtain the electric field, and from the electric field, basically, you can deduce all the properties that you want. For instance, the properties of the light at some surface above your matter surface. This you can do by applying a Fourier transformation within this plane, basically. All right, so as I said, the first step is now to build an accurate solver for this forward problem. And as motivated earlier, this we want to do via physics-informed machine learning. So we want to build a neural network replacing the simulations or modeling the simulation. And here I've included a visualization of this neural network. Maybe before we look at the neural network in more detail, let's look at the input first. So the input, the main input, is again this permittivity function in 3D space. And this we discretize basically on a regular grid, so using a voxel-wise representation of it. And the output is then also discretized in the same way, so you also get it on like a regular grid. Because this representation of representing it in a voxel-wise manner, this is of course very similar on how you represent images in a pixel-wise way. And this is also the reason why the model here is adapted or inspired by techniques you're using in image segmentation, for instance. So you can see here that all of these purple layers, they are convolutional layers, now in 3D, with some convolutional kernel acting locally on your inputs. And yeah, hence you also include sort of the locality of the problem into the neural network architecture. And then all of these convolutional layers are arranged in this unit type form, which, as I said, is very common in image segmentation tasks and works well there. All right, so this is the permittivity input. Also, additionally, you have the inputs of the parameters from the incident light. So these are just scalar parameters, in this case, lambda and phi, so the wavelength of the light and its incident angle. They enter the whole net via a smaller neural network and then gets added to one of these layers of the unit. Okay, so in total, this neural network has now some million trainable parameters. And speaking of training, the way we want to train this is, of course, via physics-informed machine learning. So this training should essentially be based on the 3D Maxwell's PDEs. Right, and how this is realized here basically is that we take our voxel-wise discretization of the output, use basically a finite difference approximation in order to compute all of these derivatives here showing up in the Maxwell PDEs, and then we have sort of a way of assessing how well the PDE is satisfied, and this we can then use to train this in a physics-informed way as described previously. Okay. As I said, this training, however, is sort of the most crucial part of getting an accurate model, and hence I want to share with you some more details of how this training worked. So, of course, during training, you need to consider a lot of different geometry types or metasurface structures in order to be sure that your model actually learns over a variety of these geometries. And here, for sampling these geometries, how this is done is as follows. So this here shows the structure of these pillars within your metasurface, and for them you define some typical shapes in advance. They can have different dimensions, and then during training you always randomly resample these pillars. You build your metasurface, compute your permittivity function, and take this as the input for your network on which you assess the validity of the Maxwell PDEs.
But this is a 2D representation. Your structure is 3D.
This is just a top view in order to...
The 3D or topology or geometry is much more complex.
Yes, it also has a height, of course, right? So this is only the visualization of what we are considering. Of course, this is just the top view of these pillars in your metasurface. Yes.
All layers are...
At the moment, they are cylindrical, basically, yes. But I mean, still, the simulation has to be done in 3D nonetheless, because you have this height component too.
So in semiconductors, the structures that are considered are really cylindrical. They don't take into account the possible benefit of a 3D topology.
This is also done, and this is also, in fact, one extension we want to work on more. In particular, if you want to actually manufacture these pillars, I mean, you can't make them perfectly straight, of course, right? I mean, yeah, and this is also one aim that we want to include this in the model. But for now, we're assuming basically that they are cylindrical, as you said. But nonetheless, the simulation is done in 3D, and yeah, you also have sort of the height component, which you don't see in these top view visualizations. All right. During training, we are considering a few million of these different or randomly sampled variations on which we assess the Maxwell PDEs. The same random sampling or similar random sampling we also do for the parameters, although this is of course simpler because these are just scalar values. The training itself is then conducted via the Adam optimizer, which is fairly basic, of course, in this context, for 500,000 epochs. So this then takes between probably half a day and 1.5 days on one of our GPUs. And you can see here in the loss curve that the loss for all of these different components of your Maxwell PDE, that this goes down nicely, right? I mean, of course, this is oscillatory or somewhat noisy because you always randomly sample these geometry on which you assess the equations. But still, you can definitely see this trend down. And also you can see that this goes down when you look at additional test cases. So there you assess the loss. This is this validation loss shown in pink here. And also if you always look at or compare this with numerical solvers, then you can also see that this goes down during training. So you can deduce that your model learns something meaningful here during this training process. And this can be further seen by looking at the results of the final model. So here I've included some comparison between a classical numerical solver, the waveguide solver in this case, with the prediction of our neural operator. And yeah, you can see already from these images that they agree to a high extent, and also that the difference is 3 to 4 orders of magnitude smaller than the output size. And here I have to say that this accuracy really is competitive with other models you find in the literature, also ones which are based on data during the training, or which are all using data during training. However, one point I have to emphasize here as well is that this physics without machine learning model actually also works in extrapolation cases, right? So at the moment, or here to the left, I only considered surfaces of this structure here, which is a similar form you could also encounter during training. However, of course, in reality, you might encounter also something different, something more noisy. And here we see that basically the error is of a similar order of magnitude. So it really excels at extrapolation, and this is also one key advantage offered by physics for machine learning, that the extrapolation usually is better than if you just learn by data. Okay, so that's that regarding the accuracy, also the speed up. I mean, once you've trained the model, then to actually compute these electric fields then only takes below 100 milliseconds, which is an immense speed up compared to classical numerical solvers. Of course.
So these solutions you are plotting there, they are low frequency, high frequency, or so to me it's a bit. I don't expect Maxwell to do the same if you put two different geometries, right? So in wave-like processes, waves are very sensitive to obstacles and heterogeneities and interaction. So one will expect a very different response when you change the geometry of the, or not.
I mean, in this case, the wavelength of the incident light, this is fairly similar in these cases here.
So why do you expect the same model to give you accurate responses for both situations?
So for both high frequency and low frequency,
No,
or
the two different shapes. You said that you train the model with shapes like this plus-like shape, and then you modify the shape into this other one, and the model performs still well.
yes, but I mean, this is precisely what the model does by learning it in a physics or training it in a physics-informed way, that it can also extrapolate to things which are unseen. Of course, if you
But in the model, there are free parameters for the geometry of the obstacle, or not?
I mean, in the model, the geometry of the input basically. So this is here the input of the geometry, and this enters the neural network, and all this is trainable, of course. Here, everything within these layers.
So, but you say that you train for some given geometry,
Yes.
and then you modify the geometry, and the model still provides a good approximation of the solution.
But this is, of course, precisely the goal that we have, to have a model who also works in extrapolation tasks. I mean, because it learned this from physical laws, right? I mean, we're not just prescribing any...
How does the model learn the dependency on the geometry? If you don't provide sufficient input, geometric input information?
I mean, here, the geometric information is processed in a local way also in this case, right? So you have some locally operating kernels which analyze in a way the input geometry locally. And I mean, for this, if you have seen enough local behavior, then you could also extrapolate to other behavior, right? But I mean, this is the aim for all of these machine learning models, to sort of, I mean, you can't consider everything in training which you want your model to perform at afterwards, right? So being capable of some extrapolation is sort of always the goal. And I mean, for us, this is also one main motivation of using physics-informed machine learning, because it has been shown for a lot of problems that extrapolation is better if you use the physical laws compared to when just using data for the training.
Yeah, I mean, the physical model introduces some filtering somehow, right? So it reduces the complexity of the functions you are considering, for sure.
The slide 13, I afraid we see very negative time, because 10 milliseconds minus 90. And model requires approximately 10 minus.
So here in the orders of magnitude, you mean, or? Yeah, I mean, so I'm now comparing these two errors with one another, right? So this is sort of the regular shape, which has the error below. I mean, these are just arbitrary units here, so this value doesn't mean anything actually. And here we actually give the percentage values, and there the orders of magnitude are similar. All right. So that's that regarding the forward solver. So now we have a solver, and if you input sort of the shape of the metasurface and the properties of the incident light, then it can now accurately tell you the properties of the transmitted light. But as we discussed earlier, this is not our sole aim that we want to follow, but we also want to generate these metasurfaces, right? So the actual application problem is that someone describes to us, okay, what are the properties of the transmitted light, say the transmittance and the phase shift of it, and your task is to design a metasurface which yields these properties. And this can, for instance, be done via generative AI methods, and the most common way I would say to do this is via GAN methods, generative adversarial nets, which I don't want to explain in too much detail, but the main idea here is that you have this generator neural network which you want to train, and what it gets as an input is the spectrum of the light, so basically the properties of the output light, the transmitted light in a sense, and its output is a metasurface design corresponding to this to these properties of the transmitted light, right? So basically it is the inverse of what we've considered so far, but this is actually what you need, right? So you want a model where you can input the properties of the output lights, and what it should output is a metasurface which has these properties, or which corresponds to these properties. And yeah, you can train this in this way, but I won't explain this too much. I would just want to say that in order to train this, you need, of course, some database on which you train. So this needs to be generated. So these are pairs of metasurface designs and the resulting light spectra. So also to generate this data set, you need a lot of simulations. And also, more crucially, if you want to train an accurate generator, it really helps to always check whether the predictions of the generator are physically consistent. What I mean with this is, so you input the properties of the output light, and the generator generates a metasurface. It thinks corresponds to this, but it makes sense to always check during training whether this predicted metasurface actually corresponds to these input properties, right? So to always guide the model in a physics consistent direction. And if you do this, of course, during training, you need a lot of simulator runs. So you need to simulate this problem very, very often. But still, this immensely improves the performance of this generator neural network. And yeah, we've done this, and this took around 400,000 of these forward simulations to do so. But yeah, this trained generator network then can actually generate these metasurfaces, which was the initial goal. Right, so here in this case of these described or prescribed output properties, it can generate a variety of metasurfaces which actually have these properties. All right, so I said this requires 400,000 simulations, and if you now look at the time, so you compare the times this takes if you would use a classical solver for this and compare this with the physics-informed neural operator, then you actually see that this definitely makes up for the training time of the physics-informed neural operator, right? So you need to invest the effort of training the operator once, but to always run these simulations, both for generating the data set used for the generative networks training, but of course also to always do these repeated runs in its training, there you save a lot of time from having this neural operator who can do these fast predictions. So takeaway from this application is, okay, these physics-informed neural operators, they offer an immense speed up, which you can then use to focus on more advanced inverse design techniques, right? Because if you wouldn't have the physics-informed neural operator, during this generative design via classical solvers might just take too long if this requires more than a week to generate such a design. Yeah, and also what we discussed earlier is that these physics-informed models, they excel at extrapolation, and also for this entire training scheme, so both for training the surrogate model and the generative network, no data at all is needed, right? This is all directly based on the physical laws. All right, so to wrap up this part on the nano-optic applications, let me briefly discuss further directions we are exploring in this direction. One is to use different representations of the input space, basically. So, as I said previously, for now this is based on regular grids, but you can also use, of course, point clouds for this. For instance, this has the advantage that you can increase the sampling close to sharp edges within your input. Yeah, this requires then, of course, also different networks. For instance, point nets are very well suited to handle point cloud inputs. And this has been done in this application, mainly by my colleague Leon. A second direction we tried is to use different inverse design techniques, right? So not to use the generative adversarial network approach, but to use a reinforcement learning-based approach. So there we did a collaboration with our reinforcement learning expert Rodrigo and developed a reinforcement learning-based agent who develops these or who designs these meta surfaces also by integrating the physics-informed neural operator. And lastly, this has now all been focusing on the meta surface application, but in fact you can also use similar models or a similar neural operator to describe processes in EUV lithography, so lithography processes essential for state-of-the-art semiconductor manufacturing. And yeah, this has also been done in several publications by Vlad, and we also have a patent on a physics-informed neural operator for this application together with an industry partner. All right. That's that regarding the nano-optic application. The second application I want to discuss in more detail is from the field of battery modeling. And this is done mainly by my colleague Philip, who also is here. Yeah, so the situation here is that at our institute, we also have one department for intelligent energy systems. And they are successfully developing this BMS, this open source battery management system here, which, for instance, is integrated into electric cars. And what such a BMS does is it constantly measures the properties of the cell, like, for instance, the current you apply, which is applied to the cell, or the output voltage or the temperature. And from these measurements, it aims to estimate the states or different states of the battery. So for instance, the state of charge, how full the battery is, the state of health. So for instance, how much capacity the best battery is left compared to the beginning of its life, and so on. And yeah, these estimates are then used to basically control and balance the behavior of the battery during its runtime to prevent failure modes and other unwanted behavior. All right, so here mainly our focus is to help estimating these states of the battery more accurately. So let's again discuss how this can be modeled mathematically. So you have your battery, and let's here focus on the state of health, which is more complex. So how much capacity your battery has left compared to the beginning of its life. In our model, this state of health is directly related to certain electrochemical parameters of our system. So for instance, the diffusivity within the lithium battery and also other parameters. Unfortunately, in reality, you cannot measure these parameters directly. But if you would know the values of all these parameters, you could deduce the state of health in this model, right? So our aim is to estimate these parameters here. But
the telephone says, right? So the telephone says what is the quality of the battery, no?
It usually, on my telephone only says the state of charge, so how full the battery is.
I think they also tell how healthy the battery is, but I don't know exactly what they do.
Maybe you have a more modern phone than I have, but...
So I think there is some more, right? That in battery, well, I'm not too good.
Yeah, but this is also then precisely based on such models, which estimate precisely the state of health. And of course, in electric cars, this is more crucial because there the battery is sort of the essential part of the whole thing.
I would say that this cannot be measured directly. This
Yes.
cannot be done indirectly.
Yes. So what you can measure actually in this model and also, of course, in reality is if you apply some current to it, and you have these electrochemical parameters, both of these influence the voltage, the output voltage of your battery. And this you can measure directly. And sort of from this mapping, you have to estimate the values of these parameters, right? So by varying the currents and, if you can, the parameter values, seeing how this influences the output voltage, this you can measure, and from this you have to estimate these parameter values actually. And this is also what's probably done in Enrique's phone. When he gets this information. All right, so
Here mine it says, which is not a good news, mine it says your battery battery's health is significantly degraded.
Oh.
So it has some internal measure. Maybe it's doing this.
Yes, it definitely does something like this, yeah. All right, so mathematically how this can be modeled, and here we are focusing on a simple model for this, is by this single particle model, which consists of concentration functions for the anode and the cathode of your battery or of your cell. And each of these concentration functions, these are these CJs here, they solve this heat equation or this radial heat equation in the first line. So you have two heat equations for your two concentration functions. Due to the symmetry, we assume in our model we have this symmetry boundary condition in the center of our cells. We also have an initial condition here for these concentrations. And most crucially, we have this Neumann boundary condition here at the surface, so at the outer edge of these of the anode and the cathode. And here you can see that in the outer boundary condition, the input current enters the equation. And you can also see a lot of parameters which basically directly depend on these electrochemical parameters, right? So these parameters, they also affect the outer boundary condition, they affect the initial condition, and they also enter here the equation via this diffusion constant. All right, so that's the model we have, and the first thing we again want to do is we want to have an accurate and fast surrogate solver. So if one prescribes the input current and the parameters, we want to be able to compute the concentrations, because if we have the concentrations, then we can do an explicit post-processing, basically telling us the output voltage, which corresponds to the actual measurements. All right, and again, we will do this via a machine learning approach. So we again represent the sort solution as a neural network. Here, the main input, as I said, is this current profile, which gets discretized again on a regular grid. This here means that we evaluate it once every second over this time frame here of 10 minutes of the current profile. And this discretization of the current profile then gets manipulated or gets processed by this one neural network, the branch neural network, which then gets combined with another neural network here at a later stage. So this structure of having two separate neural networks of this form is called a deep ONet or deep operator neural network. And the idea here is that the current profile and the coordinates of your solution, and they affect the solution, of course, in very different ways physically, right? And hence it makes sense to also keep them separate in the architecture for as long as possible and only combine them at the end, in this case via an inner product of the outputs. All right, so that's the dependency on the profile and the coordinates, but of course also you have the parameter dependency. So in this case, we want to analyze the influence of 8 scalar parameters entering the equation or the model in different ways. And this total model here has around 1 billion trainable parameters. And the training is again based on physics, right? So we are using the concentration outputs in order to compute the physical loss terms, in this case mainly the PDEs, the both heat equations, and these outer Neumann boundary conditions here. And then we combine this all in one single composite loss function, which we then use for the training of this. All right. Again, let me discuss the training in more detail, because again, you have to sample or you have to assess the validity of the physical laws on different inputs. For the points or for the coordinate and parameter space, this is rather simple, right? So you just randomly sample points where you evaluate all of these laws. But what you also have to do now is you have to choose which of these profiles you want to consider during training. And in this case, we've chosen this function space here of these Gaussian random profiles, which basically are randomly generated function with a single scalar parameter telling you how oscillatory these functions are, right? So this ranges what we're considering in training from profiles of this form here, which are very regular and not so high frequent, up to these high frequent profiles shown here at the bottom. So during training, in this case, we at the beginning randomly sample 10,000 of these profiles, and then we randomly pick some of these during training to assess the physical laws. And the loss curve in this case looks like this. So we train this again with the Atom optimizer, in this case for 1 million epochs, which takes around 4 days on one of our GPUs. And you can again see here in the loss curve that this goes down. So these bottom two curves are the PDE losses, which still go down during training, of course, a bit noisy again. And also the boundary condition loss, although it remains at a higher level, it goes down during training. More importantly, however, is that simultaneously to this loss decay, you also see the decay again in the numeric or in the error compared to the numerical solver. This is shown here in these two graphs. Okay, so during training, we are considering these Gaussian random profiles here, but I mean, this is not what we will encounter in reality, of course. So in order to assess again the accuracy of this network, we again check, okay, how well does the deep ONet or this neural operator perform on application relevant current profiles. And these include constant currents or just a constant input function. These pulse profiles are very commonly used for battery testing. So these are basically step functions. And we also included these drive cycles here, which are actually the standardized drive cycles used to test batteries in electric vehicles. And this is all used as the input to test this. And you can see here that if you look at the voltage error, then this is all, the accuracy is below 1 millivolt, which is sufficient for the application, because in these battery management systems, the measurement error usually is significantly higher than this 1 millivolt, right? So this accuracy here is definitely accurate enough. And of course, again, you get in a significant speed up compared to numerical solvers to predict this voltage. However, here, the speed up is not everything that you gain, but a further advantage of this neural operator is that you can analyze it more directly than would be possible with a numerical solver. So what do I mean by this? At the beginning of this part, I showed you what our actual goal is to estimate these parameters, right? So for different current profiles, you get different voltage outputs. And from this mapping, you basically want to estimate what are the parameter values. Now, it might be the case that for certain profile inputs, so for instance, if you just have this constant current, that your output is not that sensitive with respect to certain of these parameters, right? And hence it will be very difficult or impossible to estimate these parameters. So before attempting to estimate these parameter values, it really makes sense to think, okay, in which settings do I have a high sensitivity with respect to the parameters that you want to estimate? And I mean, mathematically, this sensitivity is, of course, just related to differentiating the total output with respect to the parameters that you want to estimate, which you can directly do for this physics-informed machine learning model, right? There you have like an explicitly given or analytical continuous model, which has these parameters as input and the voltage as output. So this you can directly differentiate in order to get this sensitivity information. And of course, now again, if you want to do this globally, right? So, I mean, differentiating only gives you information in a local sense. If you want to get like an overall picture of which setting is sensitive to which parameters, then you need to compute a lot of derivatives, right? So we've done this here by analyzing, in this case, 15 different profiles. And this already required differentiating around 2 million times in this case to get a more global picture, actually. But if you can do this, then again, you can build advanced of these estimation algorithms, right? What we've done here is we did an estimation algorithm where we first did this global analysis and picked the setting where the parameters are most sensitive in. Then in this setting, we did a parameter estimation algorithm, in this case, differential evolution. And once this has converged, basically, or once this has estimated for a sufficient number of steps, we can again looked at the sensitivity and looked, okay, which of the parameters precisely has a high sensitivity? Because if it has a high sensitivity, you can assume that it has been accurate, that it has been estimated accurately, right? And for these parameters, which are already estimated accurately, you can basically freeze them and then continue from the start again with the reduced set of parameters. So in this sense, you can sort of iteratively estimate the parameters which we also showed yields more accurate results than just doing it naively in some setting, which you don't know in advance how sensitive everything is. And here again, you can see now that although the pre-training time required for the neural operator, you can see the immense speed up, of course, because differentiating a numerical solver is complex. And I mean, here this is even done via like a finite difference scheme, this differentiation. And you can see here now the immense speed up offered for this by the neural operator. And of course, also for the other parts of your parameter estimation algorithm. So again, here the takeaway is that the surrogate solver offers a significant speed up for this parameter estimation algorithm. And here in this case, you also see how you can use the properties or that you can also use this differentiability property, right? So you can easily differentiate this neural operator once you have it in order to use this information further in your optimization algorithms, basically. And again, you have high extrapolation, which you already need because you want to be able to analyze a lot of different current profiles in this. And also, again, no data is used for this. Okay, further directions that we want to tackle in this application are to increase the model fidelity, so to go beyond these two heat equations to more accurate models, which are, of course, then also more complicated. And also, I mean, at the moment, this is all more academic, the profiles we are considering. And we also want to include real measurements in the validation and estimation algorithm soon. All right. Looking at the time, I will skip the next two applications, which are about edge devices, right? So if you want, you can make these models very small to also be able to run on edge devices. And what I also said previously is that you can combine data and physics directly in the training to get sort of calibrated models once you've trained them. Yeah, but nonetheless, let's jump to the conclusions directly. So hopefully what you can take away from here is that these scientific machine learning approaches, that they really offer you or give rise to improved simulation methodologies, right? These neural operators, they take some time to train, but once you have them, you get an immense speed up compared to classical solvers, and you have more ways to directly analyze them. So for instance, to differentiate them, which you can then use for the sensitivity information. Then what I showed is this physics form training, that although this can be challenging, of course, to get accurate, if you succeed to do so, this leads to accurate models, which particularly excellent extrapolation tasks beyond the training or the data, or not the data, but the settings considered during training. And lastly, what I also wanted to show here today is how you can integrate these neural operators then in optimization methods. And now you can really focus on building advanced optimization methods, which wouldn't be feasible to do with classical numerics, right? Because either this just would take too long, or because, for instance, this differentiability information would not be available. So building these neural operators, these physics form neural operators is the first step. But then you really have the chance to improve optimization algorithms immensely. So for instance, inverse design, you can now focus on building advanced algorithms there. Parameter estimation, you can now use the sensitivity information, and of course also further optimization algorithm like topology optimization. All right, so my very last slide, but this has already been said by Enrique, that we are actually rather close by. So you can see here, this is our institute, and this is where we are located at the moment. So this road should also be snow-free, more or less, at the moment, so it is safe to travel there. And you can see that just a few minutes away, our institute is located. And of course, in general, we are always looking for students in different positions, and of course also are always happy to explore new research collaborations. So if you're interested in these topics I presented today, feel free to reach out. And of course now, thanks for the attention, and looking forward to the discussion.
But you know, mathematicians are shy.
I know. I'm also shy.
You have
yeah.
been shy in the past. Now you are not. So I'm sure there are plenty of questions. Yes, Sigia.
resolution free in time. So I'm not sure whether in this problem, like in this project, has this problem for the resolution.
Yep, this is definitely a problem here because, for instance, if you want to increase the resolution in one part, for instance, close to some sharp edges or so, you have to increase the total resolution. And this, of course, then increases the effort for training and so on immensely. But for this reason, actually, we also followed this this more resolution-free approach, which I mentioned here, based on these point nets here. So here the idea is to use a point cloud-based representation where you can, of course, increase the sampling density in some regions where you want to. And this is then processed by what's called a point net, which is specifically tailored to handle these point cloud inputs. And yeah, we did this precisely due to this reason. Yeah, but if you're interested more, then you can also discuss it with Vlad in more detail. So he's our expert on this nano-optic application. And yeah, it would maybe be good if you discuss this with him.
Any questions, comments? So you mentioned, I think, in the beginning, finite differences, right? You said the magic word finite differences. I remember when I was a student, one of the hot topics for Maxwell equations was the development of very sophisticated or well-performing mixed finite element method. So somehow in all these methodologies, can you use the know-how in finite element theory, or is it important that everything is put in this context of finite differences?
Difficult to tell, I would say. So definitely, I mean, one main direction the community follows is trying to learn as much as you can from what has been learned in the classical numeric sense, right? So let it be finite differences, finite elements. Also, further developments go in the direction to sort of integrate these methods into finite element solvers. Or, for instance, if you have any iterative scheme, then you can use these predictions to make like a first guess and then be able to converge quicker or so on. Yeah, the other way around is of course also important, but more difficult, I would say, right? So, but also, I mean, things like where to sample points, where to increase density. I mean, this is something where one definitely learns something from finite elements or other numerical methods. Yeah.
But I understand that when you adopt this finite difference perspective, the nice thing is that you can also, for instance, record the shapes of these chips, right? So you are evaluating them. Something that, from a math perspective, is probably challenging is try to understand well. For instance, in this, if you are
Conference or?
Yeah. Do you have a class or?
Yeah, I do.
At what time?
Now.
Okay.
So
Okay.
15, but I don't know
So
if there's another.
then we can continue then.
We will continue.
Yeah.
We can also continue during lunch if you want to.
So thank you again, Christopher. So now you know each other. There will be plenty of interactions in the future, and we can continue the discussion maybe during lunch. Yeah.
Yeah, hopefully.
Thank you.